Hello and welcome everybody for this week's
Random geometry.
close to
Okay.
Infosys Chandrasekhar on Random Geometry Colloquium. Today we're very glad to have our own Babak Modami, who'll give us a talk on well-predicted geometry of triangular spaces. Thank you.
Thanks. Thanks for the introduction. Also, thanks to everybody for coming. Today I'm going to talk a little bit about the Weyl-Petersson geometry of Teichmüller space, but I think some of the terminology and the notions which I'm going to use are not that standard. So part of it will mainly just introductory and to basic notions which we are going to use, and the rest would be some theorems and maybe a sketch of a proof or something like that to see how arguments work. So first everything is going well. Okay, so we are going to talk about Teichmüller space. So then, okay. So I need to put a surface on the board. So let S be a surface of genus G with P punctures. So it's an orientable surface with genus G and P punctures. And as soon everybody knows when 3G minus 3 plus P greater than 1, we can equip this surface with a complete hyperbolic metric and work with that. So the Teichmüller, the Teichmüller space of as I said, so I'm going to maybe give some basic definitions of this surface. Is the space of all marked hyperbolic structures or complex structures. So let me write it F from S to X, where this F is a homeomorphism. And X is either you can think about it as a complex surface or a complete hyperbolic surface, and which are equivalent to each other. And we have an equivalence on this space where two of these marked surfaces, the marking is the homeomorphism from this reference surface to S are equivalent if, so let me write it here. So let's say I have two marked surfaces, then they're equivalent if F inverse OG is homotopic to an isometry. So let's say these are hyperbolic surfaces, then as soon as I have this then these are going to just determine a single point in the space, and the mapping class group of the surface. So let's actually just put it down and just take it up. Okay, so here I have the mapping class group of the surface, which is just a group of homeomorphisms of the surface up to homotopy, right? So the two homeomorphisms are considered to be the same if they are homotopic to each other. Acts on this space by remarking. So you can pre-compose your markings with elements of the mapping class group to act on in space, and on the quotient you get the moduli space of surfaces. Okay. So, and the trick was to use the last one, right? Or okay. Okay, first of all, is there any questions, or the is an isometry? So homotopic to an these are hyperbolic surfaces, and so if you can find an isometry in the right homotopic class, then they are going to be the same. Okay, so this is the general setup, but let's also let me give you one example. So when S is a once punctured genus 1 surface, which is going to look like this. So let me just draw this picture say. Okay. So the genus one with one puncture, which I'm going to show it like that. Then the Teichmüller space is going to, you can just convince yourself that every hyperbolic, so let's say this is the hyperbolic, we have this infinite cusp. Every hyperbolic structure is determined by the length of this curve and how you glue along the curve. So you have two parameters, and then the Teichmüller space. So one of them, which is just positive, the length of this, which is going to be look like this axis, and then the twisting parameter could be positive and negative. So then we have the H2, which is the Teichmüller space of this space, and the mapping class group is going to be SL2Z, and in the quotient we get a surface which looks like this. So let me draw a picture like this, because the fundamental, so when the SL2Z acts, so we have the fundamental group is going to look like this. So we have the translates of this region, so two regions which look like this, and then they're going to cover everything, and then this fundamental domain is going to be projected to this surface, which is called the modular surface, but this is also the picture of Teichmüller space modular space mapping class group for once punctured torus. So first of all, is everything clear? So now let's say and we want to do some sort of geometry or maybe on this space. So one of the questions is about the behavior of geodesics, or maybe developing some sort of coding for the geodesics on this space. So which right now we just can think about it as just upper half plane and this picture, but back of our mind we know that this is also the modular space picture. So let's say if I have a geodesic which looks like this, so this I can write a continued fraction expansion for this endpoint, which is going to so let me show it like this. So this is just the standard notation for the continued fraction expansion. And as a motivating result for this talk, so there is this result of Marsden Morse from early 1900, that if says that if this sequence is bounded, then the geodesic projects to a compact subset of the modular surface, or let us just put this MLS11. So this is a classic result, and just to giving some maybe rough idea. So this numbers which you can see actually are just supposed to keep track of the regions which this geodesic intersects, and so you also know that the SL2Z is generated with these two elements. So then practically, so if we call this maybe R and this L, so just when we follow this, let's say I have this, and let's say it's some sort of truncated picture. So when we have two endpoints, we just keep track of the elements of the mapping class group which I needed to apply to get from here to the end. Okay, so if also when we have a look at this translates of the fundamental domain, the ones which have the point at infinity in the up, they are going to be, or maybe at on the left hand side are going to be. So let's call this maybe L, this R, that doesn't matter. So then we just kind of have a sequence which looks like a L1 to the A0, let's say R to the A1 and so on. And then that's essentially that tells us that what are the regions which the geodesic intersects, and that is going to be just kind of the meaning of this coefficients in this expansion. Okay, so then there is not much of mystery. So there is just this cutting sequence which tells us what the geodesic does, and so also. So I drew this picture, but sort of we have, and I told you that the period that the Teichmüller space is H2, but H2 also has a metric, right? So it's not just a topological space. And actually, this picture corresponds to the Teichmüller metric on the Teichmüller space and the moduli space, but which has been studied for quite some time. But there are other metrics, including Weyl-Petersson metric, which I'm going to talk about that today. So which sort of when you equip the Teichmüller with that metric, it's going to be an incomplete metric. So let me just write a formula just to have it here, just to say that we know what's the actual formula. But then eventually, it's sort of we are going to use just some of the properties of the metric. So the Weyl-Petersson metric, which actually originally came out of the study of the, let's say, modular forms on the upper half plane, is defined in terms of a pairing on holomorphic quadratic differentials. Again, if you don't know them, these are essentially the tangent vectors to the Teichmüller space, or cotangent vectors to the Teichmüller space. With a pairing which looks like this, divided by rho, where the rho is the hyperbolic metric at the point which we are evaluating this pairing, and we need to look at the real part of this. And then this is a real metric, and which is called the Weyl-Petersson metric. This is the Weyl-Petersson metric on the Teichmüller space. It's kind of, you can define it on any Teichmüller space. But it depends on whether you show your metric with okay. So if you want to show it with rho square, so let's say this is the hyperbolic metric. But you can also show it just with rho, and it's just a matter of notation. Hyperbolic metric on the X, this marked hyperbolic surface. Okay, it's the hyperbolic metric on this. So sort of you define this metric on the Teichmüller space. Each point is a marked hyperbolic metric. So you take, and this is just a metric. So this is the way of some sort of contraction of tensors and so on. But in that's a more kind of hands-on form, you just to show it like this. This is going to have the two form, and you can integrate. Yeah, I have two holomorphic quadratic differentials, and then there is this method. So let's say I have let's say phi z dz squared. So this is this means and then psi z dz, and this metric is just rho squared dz squared. Okay, so then kind of if you want to just think about it, when you take the bar, so you put this here, and then you divide, you just cancel this. So you can make sense of them as contracting tensors and so on. But then you get something which is of this form, dz bar, which is a two form, so with some coefficients, and then you can integrate it and get a number, and that's going to be the inner product of these two things, and sort of this is going to be the metric. So, but as I said, through the work of several people, starting from Alfors, including Alfors, Beers, Wolpert, and several others, we know many of the properties of this metric, which are really important for us. Yeah, you could the pairing, yeah, but it's still that's but again, in what sense?
moving in the actual space means that you have a vector in the electronic differential, which basically tells you.
But then your wave, your Teichmüller metric is also like that. I mean, sort of all of. No, there you can define it as a norm. Just take the absolute value phi and integrate it. That's also defines in terms of a norm, not a pair. Some songs, yeah. So the change of, let's say, complexity or even hyperbolic metric. I mean, the either one. I mean, so it's a combination of the L2, right? Yeah, that's what. So there, yeah. So well. But again, so you should be more precise when you say change in what sense. I mean, the Q conformal changes the Teichmüller, but well, anyway, so one needs to make that more precise. But okay, so let's say we have this, and this list of properties, which I said as comes out of the work of several essentially complex geometers or analysis. That first of all, this is the Riemannian, the definition. Okay, so I put the Riemannian metric. And it's in contrast with the Weypeter with Teichmüller metric, which is Finsler. So also it's incomplete. So I just list some of the properties, and it's going to be negatively curved. And it has, let's say, cat zero completion. And so on. So it's a kind of you can think about this list of properties which this metric. Is there anyone who wants to add anything else to this list of properties, or is there any other property which you expect from a metric, or when you talk about the metric, the curvature, or maybe completeness, and so on? Questions which you ask. And okay, so now. Let's say we have this metric, which is again incomplete. So you're going to, instead of this infinite cusps, let's say cusp in let's say singularity in finite distance, and that would be the picture which we have. So and now, as I said, so let's say for S11 we have this picture, so which is let's say at least we have some sort of coding for the geodesics, and this all works for both also the Weyl-Peterson metric, both the Teichmüller and Weyl-Peterson metrics. But the question is what we can do in general. There's the same stuff for the Weyl-Peterson in this S11 situation. No, actually, so the geodesic is going to look different, but somehow you have some sort of boundary theory, and so sort of when you let's say when you look at the Weyl-Peterson geodesic, it lands at some point in infinity, and there's still when you write this thing, it corresponds to intersecting fundamental domains, but in sense of Weyl-Peterson, so they're going to look different kind of fundamental domains, but I think the whole thing is robust. I mean, sort of it works for both my metrics. It works. I mean, sort of this continued fraction. Yeah, so exactly the same thing, but sort of anyway, the picture looks different. But again, you have this fundamental domains, and you keep track of the regions which you intersect, and they correspond to the coefficients in the continuity fraction expansion. Right. That's right.
So how would you?
But that doesn't, so going to the cusp, directly to a cusp, or just landing at infinity, I guess they're the same thing, right?
So what you're saying is basically, I mean, how in the Teichmüller case you have this Kelvin hypothesis.
Also, let's forget about the inferences. We can even just have some sort of truncated picture, and just do this, look at the regions, and maybe anyway, so just send the endpoints to kind of infinity or something. Yeah, so that's a geodesically convex. So that's the geodesic. So that's also a non-trivial proved by Wolpert and other. That's part of the cat zero completion means of the everything. Yeah, it's geodesically convex as well. Which is again, I want to is a non-trivial result, but it's correct. So you get a completion strata which corresponds to the let's say at the Teichmüller level you have the Teichmüller space of where you add a number of just a stable curves. So you have a multi-curve and you introduce a pair of cusps. So if you wanted to think about the Teichmüller space and to take the Teichmüller space of that as a completion strata and just add all of these things corresponding to kind of various multi-curves on the surface. Okay. Is with the geodesic, so is that enough, or maybe it should be star shaped? I don't know. So you fix the point.
It's a point. The other point
can be joined, and yeah, you can just maybe retract it over that. Yeah, I guess that's at least one of the ingredients, but maybe you need some more also. Yeah. Right. And just kind of negative. Okay, so right, so but now so. As I said, so we have this picture, but then the question is what we can do for Teichmüller spaces in general. Equipped with Teichmüller metric, can we have a picture which looks like this, or some sort of coding for the geodesics, or maybe more, let's say it's a combinatorial description of the geodesics. I mean, to get to that, I need to kind of go through a list of the things which are kind of not that standard. I just introduce them, and then we can use those to hopefully, I mean, at least state results which look like what we have here. Okay, so the first thing which we saw, and these are kind of Mazur and Minsky made some kind of seminal work about what I'm going to talk about. So the first thing is the curve complex, which, or let's put it just the curve graph of a surface. So I'm just going to give a quick definition. So it's a graph, and the vertices. So maybe some, I guess half of the audience are familiar with these notions. The vertices correspond to homotopy classes of homotopy classes of simple closed curves on the surface, and the edges correspond to the pair of curves. So let's call the homotopy class of a simple closed curve just curve, pair of curves which can be realized disjointly on the surface. So this is the definition. So let me also just draw maybe a picture, just to a quick picture. So let's say we have a surface, and let's say, so let's say if I have, let's say we have this curve, this is another curve, and let's say this is a third curve. So let's see if we call this alpha, this beta, gamma. So here gamma is so in the picture you can see is the disjoint from alpha and beta. So let's say this is alpha, beta, and this is gamma. So we can connect the gamma to this two, But alpha and beta, there is no way to realize them disjointly on the surface. So there is no edge between them. Okay, so this is just a picture, and you extend it for any curve on the surface. You just add to your graph and decide whether it's connected to some other vertex or not. And then it turns out turns out to be an infinite diameter graph, which is locally infinite. That's obvious from the picture. And so one of the results of Mason-Minsky was that although it's kind of a locally non-compact space, it's hyperbolic in the sense of Gromov, and you can use it for certain purposes. Okay, so then I need to just go here. And what was this? Oh, the middle, okay. Oh, so that's the curve graph, so I need to also to speed up. So then there is this notion of subsurface projection. So these are going to help us to get the same picture for surface for the, let's say, Teichmüller space and modular spaces in general. Surface projection. So let's say again, let me do so it's going to for any subsurface. So it's a map from the also we show the curve graph of the surface with just C S to the C of actually it's going to be the power sets of that, but let's just keep it like this, and sort of just let me just draw a picture. So when we have again surface of genus 3, so let's say this is a subsurface Y, and when we have a curve here which intersects this, I just take the endpoints on the boundary and close it up with an arc in the boundary. So either on this side or the other side, and then we have a curve which is inside that subsurface, and that defines the subsurface projection. And in the case that the subsurface is an annulus, so the definition is slightly different. I'm just going to give the picture. So you'll let's say this is this Y was a subsurface which is not an annulus. But if I have an annulus, I just take the compactified cover of the surface corresponding to that annulus and just lift this curve to that cover. Okay, so let's say what? Yeah, so the even here, so you have the two curves in the image, but it doesn't matter. So it's a coarse map because they are going to be bounded distance in the curve complex of the subsurface. So it's coarsely well defined. Okay. So let's say I have this curve alpha, and I want to project it to this subsurface Y. It just so let's say that this curve comes inside and intersects it. If it doesn't intersect it, then the projection is just empty set. But if it comes and intersects it, I just take let's say 2 points of intersection, and I close up that arc with an arc in the boundary. So either in front or in the back. So now this is going to be an arc plus an arc is a curve, and the curve is going to be a curve in the curve complex of Y, because the curve complex of Y is the set of all the curves in Y, and that's the projection. You just take the thing, just close it up to get a curve inside that subsurface. And in this situation, it's just a lift. So you just lift the thing. Let's say maybe you can draw a better picture. Just lift your. Sorry, this is let's say for some other subsurface. Let's say beta. So then let's say if this is the compactified cover, you just lift the curve to that cover, and that's going to be your subsurface projection. Okay. So, okay, so let's keep that one. So that's it. this definition. No, I guess that picture is the more useful, that the definition.
What you just program the code and you want to understand.
Okay, so we can just do that. And so then, well, okay, so this is maybe
Yeah, good to go.
down. Okay, so then this is the one in the middle. So this is supposed to be used. And then what? Then this again goes down, and I take the. Okay, so then. Okay. Okay, so now, so let me also now I can define this something which looks like this coefficients. So let's say if I have the two curves, so let's say this is actually also called subsurface coefficient. So let's say if we have two curves, then and a subsurface. So let's say for any subsurface, just the coefficient, let's say for two, let's say alpha and alpha prime, is going to be the diameter in the curve complex of the subsurface of pi y alpha union pi y alpha prime. So in other words, you just project, and as I said, this is essentially also just the distance between the projections. As I said, these are just bounded diameter subsets. So if you take the diameter or the distance are going to be roughly the same, but then this is going to satisfy also the triangle inequality. That's why we write it as the diameter. Now this is so we have this for any subsurface, we have the notion of subsurface coefficient, and now we can just hope using these coefficients have some sort of coding. Okay, so also before, so are there any questions or no? So also before moving further, so let me just do one more graph combinatorial nonsense.
Subsurfaces correspond to the moduli space.
For annular situation, right? Yeah.
These are the
Strata, right? Something. Right.
So that's the right analogy of the moduli space. There will be one
Right.
metric.
Right. That's right. So yeah, that's good. So for anyway, so maybe at some point I kind of mention that again. But okay, so everybody understood what monster. Okay. So these are, yeah, it's a bunch of definitions to what's that? For once punctured the torus, the analogy is that you have these coefficients are going to correspond to subsurface coefficients of simple closed curves on the surface. And you kind of, when you have, when you keep tracking with applying this elements of SL to Z, actually you're doing den twist about, let's say you fix two curves on your surface and you apply den twist, powers of den twist about them, and den twist, powers of the den twist.
And coding is going to be some coding of
The geodesics. Geodesics, so again, you get the same list, but
for what? The point is about. Here you're going to have
a point.
so
Uh,
here there's a boundary.
There also, I mean, sort of, you can literally think about this as a boundary at infinity of the, let's say, Teichmüller space. Also, I mean, you don't need to. Right. Also, there is a way of putting the Thurston compactification is which uses measured foliation. That's also going anyway. So if you want to,
So what is the subsurface coefficient?
is going these numbers. Subsurface coefficients are going to be this just numbers, but correspond to different annuli on the surface. When you have a puncture torus, the only possibilities for proper subsurface are annuli, and you just have different annuli, and the the subsurface coefficient or the power of the dentist corresponding to those animals. Again, so it's if you want to kind of, I guess Series has written a paper which kind of work out the detail, but it's not super straightforward. But anyway, so you can see that you have the cutting sequence and these domains, and then anyway, so you need to think about the mapping class groups either as the dentist or about different curves or just these two algebraic things which you are applying. Oh, so then there is this subsurface coefficient, and let me also just put this PANSS graph, so that this is also another combinatorial object which we use. So the vertices are going to be PANSS decomposition. And the PANSS decomposition is the maximal set of the pairwise disjoint simple closed curves on your surface. So let me just draw a picture for. So let's say this is a genus 2 surface, then a PANSS decomposition is like something like this. Or you can have some other, for example, if this is another PANSS decomposition. You have many PANSS decompositions, and the edges correspond to let me just write elementary moves. So this means that let's say you have two PANSS decompositions, and you can obtain one from the other one by replacing a curve. You're fixing all the curves, but replacing only one with a curve which has minimal intersection number with that. So then this is an elementary move, and if the two PANSS decomposition differ by an elementary move, then you can connect them. So let me just again the picture which we had. So let's say I have this white thing, and let's say if I have the yellow PANSS decomposition, which is this, so the yellow and the white can be connected because the sort of all of the curves in the PANSS decomposition are the same, but one differs from the other one with the essentially one obtained from the other one by replacing this curve with the curve with minimal intersection number, which is 1. Okay, so then you get this, and now let me actually state one theorem. As I say, most of this is supposed just kind of review of some basic notions. So that there is this result of Jeff Rock from around 2002. So we said that there is quasi isometry. So let's show it Q from the Teichmüller space equipped with this Weyl-Petersson metric to the PANSS graph, which is the metric space because you can just assign length 1 to each edge. So and here also the correspondence is the more or less straightforward. We assign to every point here a bounded length PANSS decomposition or Beer's PANSS decomposition of the surface, and this is something which relates this kind of the whole business about the Teichmüller space, this Weyl-Petersson metric, which is the Riemannian and Katsirov and others, up to this combinatorial world of curve complexes and this combinatorial objects. So that was the main results. Okay, so now here, okay, as I said, I want to keep that, but then I can erase this and then the one round 2. Yeah. Okay, so now let me actually just state this this thing again. There a lot of Brock, Mazur, and Minsky. 2009. So, which is the analog of this result of Morse, which says that for every So there are more quantifiers, but for every r, you can take it an integer. There is an epsilon positive such that if so if we have a geodesic such that all of its so this is for a geodesic. So let's say I also have just a geodesic segment. Just take this short pants decompositions at the endpoints. So the endpoints are two hyperbolic surfaces, and you can just no, it's a geodesic in the Teichmüller space. Teichmüller space, and the endpoints are so you have a family of surfaces. The endpoints are going to be two surfaces, and now you pick two short pants decompositions at the endpoints. So you have a surface, and you have a notion of short pants decomposition. And now if you have a similar condition, if all of these coefficients are bounded for proper subsurfaces of S, then this geodesic, whose endpoints are P minus and plus, this projects to the epsilon thick part of moduli space.
You have defined distance between simple closed curves.
Yeah, for pants decompositions, so yeah, so you do. Yeah, so you do it for all the curves in the pants decomposition, and actually it doesn't matter. So because they are going to they're disjoint, and again you get bonded diameter subset. And that was a good point. So I just said how it works for two curves. So but for multi curves, you do it for all the curves which are involved, and you get again numbers. But now having that been done, we have a statement which looks like this, and this epsilon thick part of the moduli space is again compact. So this is a compact set. So we have the exact analogy. So as soon as you bound all the subsurface coefficients of the endpoints, you get something which projects to a compact subset of the moduli space. Okay, so at least you see that we develop some language which kind of helps us to, let's say, have a statement which we had for just a modular surface. Okay, so let me now. So what's the now? This goes up. This goes up. Do some. Okay, so but now maybe this is I don't know. So if I get so let me also say a little bit about how the proof of this thing works. Maybe this will not going to be actual proof, but just just a sketch, and so giving an idea about what are the techniques which are involved. Sketch of proof. Okay, so actually it's based on two observations. The first one is that so I'm going to write it here. So the non-annular bounded combinatorics. So which is, so here I have the bounds. So I said let's bound all the coefficients, all the proper subsets. And when I say non-annular, it means just take the part which corresponds to non-annular subsurfaces. Just forget about the annuli, and just that is enough. So this implies that so I need to put something here that let's say a hierarchy path. So I'm going to say path between P minus and P plus in the Pans graph is stable. Okay, so for the hierarchy pattern, I'm not going to say much. So these are some just standard parts which came out of the work of Mazur-Minsky. So these are going to be some quasi-geodesics, uniform quasi-geodesics in the Pan's graph with certain nice properties. In particular, so sort of they have the so-called no backtracking property and others. So, but you can see just a set of transitive quasi-geodesics in the Pan's graph. So, which have a nice combinatorial properties is stable. So, and stability of a just in the general sense that if I take this thing and I have a quasi-geodesic whose endpoints are on this hierarchy path, then the whole thing is going to stay in a boundary of that. Okay, so this is something. So now, so actually, so now let me also draw a picture. This is going to be very kind of proof by pictures. But so let's say this is the high-Euler space, and this is the Pan's graph. And we said that we have this quasi-isometry. And let's say I have this geodesic segment, which I said with the endpoints P plus and minus. So, okay, so G, P minus, P plus. So then here we look at the thing, the two endpoints here, P minus and P plus. So these are two Pan's decompositions. So this is this P plus and P minus are just the Pan's decomposition corresponding to the endpoints of this geodesic. And so and the whole thing by this quasi-isometry is going to map to a quasi-geodesic, but also we have the let's say the hierarchy path which connects this two. And then now that stability means that these two essentially kind of stay in a boundary of each other. And in particular, we can just for subsurface coefficients, we can go between these two paths. So if I measure, let's say, I have some subsurface coefficient, maybe somewhere here is developed, somewhere here is going to be developed also to be seen along the hierarchy path. Also, that's one ingredient. And the other one is that sort of is about this is going to be more geometric. That let's say, let me put it in the excursion into the thin part. Again, is the part where the injectivity, we have the surfaces with the injectivity reduced smaller than some given constant, into the thin part over short time interval correspond to developing let's say den twist, or having a large subsurface question about some curve. But a curve. Again, in the picture, so let's say that these are the thin parts of these are the strata, and the thin parts are the neighborhoods of those. So if over short time interval you kind of deviate and go close to this thing, so you will see a high den twist about a curve. One of the curves which determine this stratum. And this is actually a non-trivial thing. It's used as Wolpert's geodesic limit theorem. So that's which is kind of anyway. So it's a geometric statement, and it's not kind of its proof relies on some limit theorem for sequences of a bounded length Weil-Petersson geodesics. Okay, so now also if you have an large angular coefficient, you will see that about so that's the point. So you will see that about this. So let's say this was my QG, and this was the hierarchy. So the point is that so you see that at the level of geodesic, but then this fellow traveling tells you that you're supposed to see that also between the endpoints of the hierarchy. But remember, hierarchies are this kind of combinatorial, kind of well-built paths that if and I said they have this no backtracking property. If you see some large subsurface coefficient somewhere along the hierarchy path, you actually see also that between the endpoints of the hierarchy path. And then again, the bond for the bonded combinatorics between the endpoints, that prevents this thing. Okay, so we have some geometric thing for the excursion and seeing some local large subsurface coefficient, but then using this fellow traveling that actually tells that you have that. And the structure of the hierarchies, you have it between the endpoints, but that's already excluded by that the condition of the bonded combinator. And that's essentially the sort of bunch of the idea. I mean, sort of the stuff which are going through in these proofs are just playing with a little bit of the geometry of the space like this, using this geodesic limit theorem or some compactness arguments and some properties of the, let's say, hierarchy paths and this kind of Mazur-Minsky combinatorial techniques. So I had that. So let me just put one theorem which involves me also. The kind of so just this is just actually I can. So I guess just well. So how much do I have? I'm 10 minutes. Okay, so then. Okay, so then let me actually, let me actually also give you one of the consequences of this theorem also. This is again going to be Brachio, Mazur-Minsky from the same time. So being able to produce this kind of geodesics with bonded combinatoric condition and so on. So they should essentially this follows from this kind of this theorem or this characterization of the pre-compact geodesics that there are compact subsets of let's say the unit tangents of the moduli space with arbitrary large topological entropy. Okay, so this is going to some topological dynamics consequence of these constructions of co-compact, pre-compact geodesics. Okay, so which I don't get. Also, the topological entropy is just a measure of how fast the number of closed geodesics are growing. So let me not put the definition. So okay, so now, so let me actually just put one. There was this conjecture also in the same paper. So, Mazur-Minsky from 2009. So about the characterization of short curve or excursion into the thin part by the subsurface coefficients. So we said for every epsilon, there is an R such that if we have a large subsurface, essentially it says large subsurface coefficient implies short curve. So let's say the boundary of this thing is getting short somewhere. Okay, or we kind of go into the thin part, and also for every epsilon, so such that if the curve gets short, let's say gamma GT, this is short, then actually, so there is a subsurface which where the gamma is in the boundary of that, and dy p minus p plus. This is large. Okay, so this was this is actually some motivation for some of this stuff, and actually Minsky had this for Kleinian surface groups, and sort of it initiated some of this interest into having the same stuff for Teichmüller geodesics. So, but then, so let me actually move to the other side. Should I move to the other side? That on the top, this into the bottom, or? Yeah, I can use this, but this is a kind of this. This has been here for quite some time. Okay, so then, but then there's the thing that this conjecture is not correct, and so the reason is that, so then there is this characterization is not correct in general. So this is me. It means, well, large subsurface coefficient implies short curve, and short curve implies large subsurface. Essentially, you have the characterization of short curves, or maybe excursion to the thin part in terms of subsurface coefficient.
If something goes to one of this data,
Right,
that's basically what you're saying. This subsurface injection is something that's going along a band thing, right?
right,
Which means essentially, if you map this whole thing back to calculus to between certain metric, it's something that's coming close to one strata corresponding to y and staying.
Right. Yeah, that might be a slightly more than that. That's yeah. So getting close to the stratum corresponds to having a large subsurface coefficient. That's okay. Also, yeah. So if that well, if the thing is getting short, also kind of you have a large subsurface coefficient.
Yeah. So here's one thing at the very early, you said this stuff about the completion.
Yeah, no, yeah, that's and the Teichmüller space is called augmentation of Teichmüller space, which is the lift of the Dolomov. With there is a Weypeter symmetry.
So you look at this completion. So since it's gas, that's what.
Right.
So in strata form boundaries
So
of what you can take a projection there.
Right. Yeah, nearest point in the cat zero space you can just right.
And so this stuff, what this thing is saying is somehow that the surface projection is large means that the.
Yeah, you don't open it or you again don't backtrack it afterwards. So if you spend some time close and develop some large subsurface coefficient afterwards, you cannot kind of just make it shorter.
Go back and come back to
Yeah.
the same specification.
That's more, yeah, the moral thing. Yeah. But again, it's not correct. So let's not do so. And then there are with explicit examples. So you have a sequence of Weypeterson geodesics such that let's say L gamma. This is this thing goes to 0, but we at the same time we have a what dy p minus n p plus n. So these are again the Pans decompositions of that are uniformly bounded below. Okay. And sorry, and at the same time, we also gamma is inside the boundary of y.
This is proving the second one, right?
It's proving the. Let me see. So we have a sequence such that the disk we're going to 0, right? But right. That's right. Maybe let me see. So, but large. What's that? Is there any like what's that? Bounded below. So no bounded above. So these are bounded, but this thing goes right. But anyway, so but the proof also uses some similar kind of ideas and some more souped up version of those. Anyway, so I think yeah, on the top. Well, I put it there, I'm not sure. So let's say, I think, no, actually, if, yeah, then that might be still correct. So I'm not sure. So let's say that this is, yeah, so let's say maybe we did, let's say this part is not correct. Okay. Yeah, so. I mean, it requires actual proof. You cannot give some counterexample, right? Well, actually, I think I'm also sorry, my time is over. Right?
No, that's okay. So let's thank the mark. Any questions from our live audience or audience of the zone?
They're leaving. So,
Then you also mentioned about the organization of the Asian or the
right.
that's saying that I mean, if you're bound, the subsurface positions are bounded below. So you're
On the above. Bounded above. Right.
It's staying far from it.
Right.
Then.
Yeah, that was this Brock-Maser-Minsky. They already proved the analog of the thing in for any modulations.
Because that for the continuous fashion, it's saying the coefficients are bounded, it's saying that it's badly approximated by that. It doesn't go to the customer.
Right. I mean, for bad, it has some sort of more kind of precise
Yeah.
kind of interpretation. But yeah, maybe you can take a look like.
One comment, I mean, it's basically regarding this hierarchy part
Right.
which we are using. And I think part of it is happening basically because there's this intersection pattern of the cusps,
Mhm.
which does not happen in SL2C. That's a rank one phenomenon, this is a kind of a higher rank phenomenon than the cusps. And so the hierarchy paths is, they are quantifying the intersection between the cusps. Right? I mean,
In some the curve complex itself somehow quantified.
so essentially, I mean, if you have a, so your business is going to go through or that goes to a sequence of cusps
Right.
in the universe. And so when it moves from one cusp
Right.
to another cusp, that's this switch in the
Right. So that's this element removal. So whatever.
element. And how much it is traveling along the cusp is given by a subsurface.
Right.
Would that be a reasonable way to think of hierarchy paths, for instance?
Well,
I mean, then there's nesting, that's further nesting, and so you have.
Right.
Surface protection.
so you're saying that, right? But also this no backtracking. That's important. That as you said. So when you see some large subsurface coefficient somewhere, you see that kind of at the end points also. I mean, sort of that's and that's if you let's say let's say when you have this hierarchy path and you take two kind of points to pass the composition somewhere in between, and you see some, let's say the subsurface, let's say y subsurface coefficient is 100 at the end points of the hierarchy path, you also see more again 100. You don't backtrack this thing afterwards. That's one of the key properties and so on. Which has been used on this. That's kind of also there. I mean, the large subsurface coefficient shows that there is a part which every Pansky composition contains the boundary of that subsurface. There, this kind of this thing, maybe this picture is more or less combinatorial version of this picture. Is
So what is that? The can't come very close to Phelan and go on. Stay for a long time. The background.
no. Like first of all, for hierarchy paths, there is no kind of that's just a totally combinatorial object. Yeah, but I'm saying that being short means that the hierarchy path, the Pansky composition contain the boundary of that subsurface. There is no notion of shortness, but you have this combinatory replacement that everything contains that multi-curve. It's just a compact part of in the quotient you have surface and it just maps to a compact part of that. This, oh yeah, the geodesic is not necessarily closed geodesic, yeah. Yeah, also, yeah, just, yeah. Ping is contained in a compact subset. When you project, it's in a compact subset. Yeah, you could segment an infinite geodesic or closed geodesic, anything. Right.
Yeah, there's a further question, so let's thank those.